Hello, everyone. My name is Haden Lee, and I'm an assistant professor in computer science at USF. So today I'm going to talk about my research projects, and I don't have an official lab, but if I were to have one, I would name it Game Theory and Algorithms Lab. So it would be the GTA lab. It has nothing to do with the game that some of you may know, but that's the tentative name I have for my future lab. So here's the agenda of today's talk. I'm going to talk a little bit about myself, like what I did before joining USF and what I currently do at USF. And then I'm going to talk about these research projects that I'm working on. So I learned programming when I was 10 or 11 because I really wanted to create my games, my own games, after playing computer games a little bit. It may sound familiar to some of you. And naturally, because I learned programming early on, I majored in computer science because I found it most natural. And I got stuck for many years as I was, as I went to grad school, basically. And after I finished my PhD, I joined a local startup called Moloco in 2016. And I joined as a research scientist, but the main role I had was basically data engineering job. So by the time I was leaving the company to join USF, I was managing the data engineering team at Moloco. And currently I'm involved with them on a part-time basis, but my primary job is teaching and doing research at USF. And I spend a little bit of my time during the summer at Moloco. So at USF, I teach CS 673, probably one of the most infamous courses. It covers algorithms and problem solving and things like that. And I teach that course every fall. I also teach electives, CS 686 and 486 in spring. So these two courses will be offered in spring 2021 as well. So last year I taught the same courses, data processing in cloud, and I'm going to talk a little bit about this course. So let me first talk about my research project in CS education, and this is really about how I teach these elective courses, data processing in cloud, because I believe that providing a really great learning environment for the students would be uh, the end goal of a teacher in terms of providing developing a curriculum, providing materials and resources and things like that. And there isn't an easy answer to what is the most effective way of teaching something. On the other hand, in this specific course, I wanted to make it so that I can provide a lot of personalized feedback in terms of code reviews on coding style, design patterns, and things like that. But at the same time, I wanted to save a lot of time by developing the automated grading system that can actually grade everyone's commit within a few minutes as soon as students push their work. So let me talk about some of these benefits that come with the automated grading system that I developed for this course specifically. So the first one is flexibility in the sense that when students are given a Java project that they have to work on, I would give some starter code so that they have a few Java files, some interfaces and classes partially implemented, but they have to add a lot of methods and more classes, maybe helper classes, helper methods. They may have to implement some of the abstract classes and so on. On the other hand, in real life, if you're doing software engineering, you will probably try to utilize some of the open source libraries because when other people have done the work for you, you just reuse them, especially when those libraries are highly respected and well adopted within the community. So I wanted to provide a lot of flexibility in terms of what students could do in their Java projects. So in this course, students can do whatever they want in terms of using libraries, plugins, and things like that. As long as the build doesn't break, then they can do whatever they want with their project. The grading system should be comprehensive so that it can fail most of the inefficient or incorrect solutions. So that can be achieved if the instructor actually prepares a lot of unit tests and test cases that can check for null pointer exception, corner cases, in some cases with some large amount of data to see whether the submitted code is doing something in an efficient way or not. So that worked pretty well because students would be then able to see what they did wrong in terms of whether they forgot to check for null values, they forgot to check index out of bound corner cases and things like that. The grading system should also be responsive in the sense that if a student submits their work, they want it to be graded as soon as possible because imagine yourself pulling an all-nighter. You just want to get done with this assignment. You submit your work, you get feedback within a few minutes, then you can continue working on it, knowing that you passed maybe 20 test cases out of 30. You have to work on the remaining 10 cases and so on. But if you get the response or graded feedback only after the deadline, then by the time you receive the feedback, you may not even remember what you were thinking when you submitted your code. So this is probably one of the most important things I wanted to achieve in this course through the automatic grading system, so that students don't have to wait until the deadline to get feedback. And they also get feedback within a few minutes after they submit their work so that they can resubmit without any penalty until the deadline. So one side effect of having that sort of policy is that students keep submitting their work until the deadline, and many students tend to work just a few hours before the deadline so that the grading system would have unbalanced workload because everyone tries to submit just an hour before the deadline. So that was an interesting phenomenon. The grading system should also be instructive in the sense that this is not just about automatically running unit tests and checking whether your code passes all test cases or not. So one additional feature I included was to actually provide some sort of hints. And this is how it worked. So I prepared probably between 50 and 80 test cases for each project. And those test cases were grouped into 3 different groups. So some of the test cases were sample test cases. Some of them were unlockable. A little bit of gamification here. And some test cases were completely hidden. So the sample test cases were basically the ones included in the starter code so that students can check to take a look at those sample test cases and run them locally. Unlockable test cases are not shared initially, but if your code actually fails on one of these unlockable test cases, but it passes all the sample test cases, then one of those failed test cases would be shared as a hint so that you don't completely get stuck in terms of debugging your code. You get some sort of hint, but you have to do some work because your code has to pass all the sample test cases at the very least. And because only one unit test is shared for each submission, you have to make some adjustments and modifications to your submission or your code so that you can unlock the next hint and so on. So overall, it was an interesting course because students actually didn't really rely on hints in the sense that students were really motivated to complete the assignment with fewest attempts. So nobody actually tried to abuse the system or exploit the system. So based on the commit history and also submission history, I could tell that students were more motivated to use fewer hints rather than more hints. So that was a really satisfying observation that I made. The grading system was also pretty robust in the sense that if a student's code actually does something dangerous, maybe students code some students submits a code just for fun, do something like and that would be really dangerous, right? So wanting to make sure that the grading system wouldn't fail even if something some students' code does something nasty. So for that reason, I used the Docker containers in terms of making sure that everyone's code would be run under the same environment, and it is also safe it is isolated from the grading system's main environment. In terms of accessibility of students' scores, submission history, and things like that, there was a live scoreboard where everyone can check at any time how everyone else is doing, in the sense that you can see everyone's submission history. You can see for each submission, like how many unit tests it passed and when the submission was made and so on. On the other hand, the identities of students were anonymized. So it was just replaced by some game icon, and also the names were hidden. And the reports, like the reports that contain, detailed submission data, for example, like which unit test case was provided as hint. So all those things were hidden, so that only the owner could access that. But everything else at a high level was shared, so that students could see whether a specific assignment is easy or hard, and they can tell that just by looking at the scoreboard, for example. And some students found it extra motivating because they wanted to be the first one to finish the assignment. So overall, the grading system was really useful in terms of how students were able to get immediate feedback on their work. And because I didn't have to grade anyone's code, I was able to spend a lot of time on providing personalized feedback in turn. So this was done through code reviews, and during the code reviews, I would just provide some comments on coding style, design patterns, and things like that. So for those who are interested in how I developed the automated grading system and how it worked. So here's some step-by-step illustration. So if a student submits, their code, they will, work on an assignment locally first, and eventually they will push some commits to a remote repository. The Jenkins, I used a virtual machine on Google Cloud Platform, and I used Jenkins CI to continuously check for new commits. And when a new commit is detected, then the grading system, so the virtual machine basically running Jenkins, it would pull the new commit from GitHub, and it will start grading. So in order to start grading a specific piece of code, it is going to be copied into a Docker container, and so that it is in an isolated environment. I can also control how much CPU time and how much memory the student's code could use, because I can control, I can sort of designate the upper bound on CPU or running time or the memory usage for each Docker container. And within the Docker container, I would be using Gradle to run a set of extensive unit tests, and the results would be summarized in a user-friendly report, which is basically a text file, and it may actually contain a hint if it is applicable, in the sense that if students' code passed all the sample test cases, but failed on some of the unlockable test cases, then one of the unlockable test cases would be shared as a hint. And then this report would be exported to the live scoreboard so that students could download it. So the whole process actually took between 3 and 7 minutes, and usually it was under 5 minutes. So more details of this work could be found at actually my personal homepage. So I recently presented this work at one of the conferences in August, and I'm gonna present the more detailed version in another conference next year. So this is the first research project I wanted to talk about. And for those who are interested in this type of research, perhaps you can take 686 with me and see as a user like how the grading system works as a student for you. And you can probably do an RA or TA with me to see whether we can add more features to this grading system, or provide something for students that can actually help them engage and get motivated even more. So one thing I'm thinking about doing in the next semester is to provide some sort of lightweight collaborative tasks, like that don't really affect students' course grade as much, but something that can help them get engaged, help them get motivated and have some fun with some classmates. So last year, this was purely individual based in the sense that every assignment was done individually. There was no group project or group tasks. So I want to add some collaboration aspect. So it will be more interactive than just working on assignments all alone. All right, so the second research project is a little bit more theoretic, and it is relevant to CS 673, the algorithms class. So one of the main problems I'm studying is called group activity selection problem. So let's imagine that you are trying to organize some group activities for maybe the CS students at USF. You need to assign these people to social activities, and they have individuals have their own preferences. So here we have 3 examples. So let's say we have these 3 activities like group bus tour, latest virtual reality device demo, and also chess games. So for the group bus tour here, maybe people will prefer more participants to be there because you might actually have to split the cost of renting a bus, and therefore the more people there are, the better it is for everyone, right? So under this problem, we're gonna make an assumption that people have naturally preferences over the set of pairs, like the activities as well as number of participants. So specifically for the group bus tour, people will actually want more participants to be there. For the latest VR device demo, maybe people will prefer fewer participants because if there are too many people, you will have to wait for too long, and you really don't want to wait for half an hour to try something. Maybe your limit is maybe waiting for 5 minutes. So if there are too many people, you'd rather not participate in this activity. So that's another example where you actually have some sort of preference in terms of the number of participants. Another example is chess games. In this case, you don't necessarily prefer more people or fewer people, but perhaps you prefer a certain number of people in a range because you prefer to have a certain number of people, like between 8 and 16, because that would be ideal. Like, you can play with many different players, you can, learn about them, you can, socialize, but at the same time, your preference may not have to be, exactly this interval or a range. So as long as there are enough people, but not too many people, you'd be really happy about participating in this chess game activity. So through these examples, I think it makes sense to assume that people have preferences not only over the set of activities, but also exactly how many participants there would be. So given such preferences of everyone, your goal as an organizer is to assign people to these activities so that everyone, given the assignments that you created, everyone would be happy about the final assignment in the sense that they would be happy to participate in the activity they're assigned to because that is within their preferences. So unfortunately, the problem that I just described is actually empty heart. For those who don't know what this means, it means we just don't think that we can design a polynomial time algorithm that can solve the problem. On the other hand, even though it is NP-complete, we can try to add some natural restrictions to the problem and see if this problem becomes any easier. So one example from the group bus tour case, if everyone prefers more participants than fewer participants for every single activity, then perhaps the problem may become slightly easier, right? Because we are only considering this special case. And likewise, if everyone prefers fewer participants than more participants, likewise, we can try to analyze how difficult or complex the problem becomes. One slightly different case would be if we have multiple copies of the same activity, meaning perhaps we are only organizing group bus tour activity, but we can rent any number of buses. So we have sufficient number of buses to rent, and it's just a matter of whether people have people may have still preferences on the number of participants that they go together on the same bus. So given that, can we actually solve this problem? And in this case, the answer is the third one is probably the easiest between among these three different subcases. And more importantly, if we are looking for a solution of certain size, meaning we don't probably want to, we may not necessarily want to assign everyone to a specific activity because perhaps we have some budget issue. We can only assign up to 50 students to some of these activities, and the remaining students will have to do something else. Like they will maybe meet with their friends, they will just tour around the city on their own. But due to the budget reasons, maybe we can only assign up to 50 students instead of maybe 200 students. If that's the case, then the problem changes slightly because now we are only looking for a specific assignment where we assign up to 50 students, but no more than that. And that kind of, that introduction of parameter in terms of the size of a solution can actually help us find practically useful algorithms, even though the underlying problem is NP complete. And one main research project that I'm working on is basically trying to figure out, where this each of these problems belong to. So, for example, in these different settings, I can probably say a specific problem belongs to the class FPT, which stands for fixed parameter tractable, meaning if we assume that a specific parameter is fixed like a constant, then it is, we can design a polynomial time algorithm. If a specific problem is in W1 or W2, then we are essentially saying that it is actually slightly more complex and so on. So we have, for those who are familiar with P and NP, we have a number of complexity classes in between. So one of the things I'm trying to do is to classify different variations of the group activity selection problem into these complexity classes. And mostly the focus is on some of the lower level classes, FPT, W1, and W2, and so on. So if you're interested in this type of research, like designing algorithms, proving that some problem is NP complete versus something else, then this is a really fun project to work on. It is rather theoretic. It doesn't involve writing any code, but I have worked with two students so far, and it was really fun to work with students on this research project. So this is something I'm actively working on. And on a related note, for the same problem, I have a different perspective. So instead of proving that the given problem is NP hard or a given problem is, say, FPT and so on, we can think about game theoretic setting as well. So for those who are not really familiar with game theory, that's totally fine. I will just try to illustrate a point through an example. So you may recognize some of these characters that I have on my slide, but it has nothing to do with that specific game that you have in your mind. So let's say there are three people here, and they have some specific preferences in terms of the assignment. So we have two activities in this example. Oops. So two activities, A and B, and we have three people, orange, cyan, and purple. So they are thinking, each of them has specific preference. So the first one here, the orange person, this orange character prefers to participate in activity A with two people, meaning including oneself. So with someone else, that would be the best outcome. So that would be the best outcome for this person. And this person prefers, is still okay with everyone participating in A, so three people basically. And all other cases, this person doesn't really want to get involved, meaning, so this empty set notation, this simply means this is the baseline utility. So the way to interpret this preference is that the best outcome this person wants is actually to participate in activity A with someone else, so it would be in total 2 people. The next best outcome would be to participate in A with 2 others, so all of them, 3 of them. And those 2 are the only outcomes that this person prefers over the baseline utility of, say, doing nothing. So specifically, participating in activity B alone, participating in activity A alone, participating in activity B with someone else, participating in activity B with the other 2 people. These are all like, unwanted outcomes for this person. This is what this sort of inequalities imply. For the second person here, purple, this person prefers to participate in activity A with everyone else. So this would be the best outcome for this specific person. And the second best outcome is actually to participate in activity B alone. Maybe this is the VR device demo activity. So if there's no one else participating in, then you can actually try it out for as long as you want, right? So this is the second best outcome. And all other outcomes, this person doesn't want to be assigned to A or B if neither of these is realized. Lastly, the third person equally prefers to participate in activity A with someone else or with the other 2 people. So it doesn't really matter to this person whether there's one other person or 2 other people, as long as there is someone else and this person participates in activity A. But all other cases, this person doesn't like it. So from the organizer's point of view, there are sort of best solutions in this case, and there are 2 different solutions. So one solution would be we assign orange and cyan and purple, all of them, to activity A. Then as a result, all of them will participate in activity A together, and therefore there will be 3 people, right? So from orange's perspective, this is the second best outcome, but it's still a good one because the person orange still wants to, the orange person still prefers A3 over doing nothing or the baseline utility. For cyan and purple, for both of them, it is actually the best outcome. So in some sense, this is probably the best solution we can hope for because there's no way to there's no way to guarantee the best outcome for everyone involved in this specific example. The other solution is similar in that we can assign orange and cyan to A. So both of them will participate in activity A, but we assign purple to activity B. In this case, purple will be alone in activity B, and orange and cyan will be in activity A together. So in this case, the situation is slightly different. So for purple, this is the second best outcome. For cyan, this is still the best outcome. For orange, this is the best outcome. So these 2 solutions are comparable in the sense that 2 people get the best outcome they wanted, and 1 person gets the second best outcome they wanted. So these 2 solutions are maybe equally good, right? So from the organizer's point of view, either solution looks fine. It's just a matter of whether you give the second best option to orange or the second best option to purple, but everything else is the same, right? So with that in mind, let's actually talk about some game theoretic situation. So let's say we have 3 candidates, A, B, and C, and we're trying to vote who's going to be the leader of our group. We have 201 voters, and exactly 100 voters prefer A the most, and we know that they will certainly vote for A. We also have 99 other voters who prefer B the most, and they will certainly vote for B. Now, you and I are the other 2 voters, and we both prefer C over B over A. But as we know, C is gonna lose anyway because about 200 voters will vote for either A or B anyway. But we actually prefer B over A, so it's actually better to write in B rather than writing in C, right? Even though we prefer C the most. And this is one reason why people act in a way, strategically. So in the sense that even though our true preference is to have C, elect C, we want to change the outcome because if we were to write in C, both of us, then A will win because A gets 100 votes versus B getting 99 votes. But if we write in B, we can change the result. We can change the outcome because 101 voters will be writing in B, and B will get 101 votes as opposed to A getting 100 votes. So obviously, if we are rational, then we will both write in B or vote for B so as to change the outcome. And the assumption here is that obviously these 199 voters are going to vote for A and B respectively, regardless of what we do. Now the point here is that even though we truly prefer C over B, because we would rather we'd rather have B as the winner as opposed to A, we actually want to change the outcome by reporting that we prefer B, right? So this is a contrived example, but this is exactly what happens when people have ways to manipulate the outcome. And let's go back to this example. So let's think from this orange player or character's point of view. Now, as I mentioned earlier, we have two probably comparable solutions, but these two solutions are not comparable for the orange character because in solution one, we assign all of these characters to activity A, resulting in the final outcome of A3 for everyone. So for cyan and purple, that's the best outcome. But for orange, that would be the second best outcome, right? In the other case, orange actually gets assigned to A, cyan also gets assigned to A, so they both get their best outcomes. But purple is assigned to B, which is the second best outcome. So from orange character's perspective, solution one is better. Oops, sorry, never mind. Solution two is better, right? Because you get the outcome that you want more than the other outcome, which is A3. So orange can think about this, like knowing that purple and cyan have these preferences. Orange may actually lie about his or her preference in the following sense. Instead of reporting that orange wants to have these two outcomes and in this order, he or she can actually lie and say, you know what, I don't actually want to be assigned to activity A if there is going to be 3 people. And this is actually my preference. So effectively, orange character is lying about the preference by excluding one of the, least favorable outcome. So if the organizer didn't know about the true preference, and this is the sort of preference the organizer receives from the orange character, then because of that, now the first solution here is no longer a valid solution because A3 is not something that orange is willing to accept. So this is the only solution that seems good. And therefore, orange is actually manipulating the organizer to choose solution 2 over solution 1 by simply lying about his or her preference. And this is exactly what happens in a game theoretic situation. So players can act strategically because they want to change the outcome in a more favorable way. And the organizer, without knowing that, organizer may actually be manipulated and choose the outcome or solution that the manipulator wants to have. So this is something I study in the group activity selection problem as well. So the kind of questions I ask are, if players can act strategically, then can we actually prevent that from happening by somehow incentivizing them to reveal the truth? So maybe when they reveal the truth, we try to accommodate their requests as much as possible. Obviously, this is not always possible, and there are ways to prove that it is possible versus it is impossible. So this is one of the other research projects that I'm working on, but in the same problem, so corrective research problem. So in summary, I have two different aspects, and this is partly why I wanted to name my lab, unofficial lab, as Game Theory and Algorithms Lab. So if players can act strategically, we want to find ways to incentivize them to reveal the truth somehow, and we want to also know whether the computational problems are easy or difficult, given that players are telling the truth, and that would be more of algorithm design and complexity analysis. And these are the things that I'm working on in the same set of problems. So here's the third research project I wanted to talk about, and it's called Fair Attribution in Digital Marketing. And this is relevant to what I did before joining USF, because Moloco is a company in the mobile advertising business. So this was actually inspired by some of the work I did at Moloco. So for those who are not familiar with mobile ads, let me tell you a little bit about it in a simplified version. So every time you open an app, that specific free weather app, radio app, or game app that you use and often see those ads. So every time you open an app, that specific app actually sends what is called a bid request. So it's just a HTTP request to exchanges, so mobile advertising exchanges like Google edX or Twitter Mopop or Unity exchanges and so on. So those exchanges actually collect what's called a bid request. And as soon as they collect this bid request, they're going to broadcast that bid request to bidders. Usually, they are referred to as demand side platform, in the sense that they are the ones trying to buy this opportunity to show an ad. So the bidders then, after receiving the bid request, they place bids, by responding to exchanges specifically. So they respond by specifying the URL to an image, audio, or video, so that if they win, those images or audios, videos will be displayed or played on the user's device. They also obviously have to write in the price, like they are willing to pay, and the exchanges will somehow declare the winner. Obviously, whoever is the highest will usually win, except for some cases. So exchanges declare the winner, and the winner gets to sort of display or play one of those creatives like images, audios, videos in the free app that you just opened. All of this, the whole thing, has to happen usually within 100 milliseconds or sometimes up to 150 milliseconds, because obviously if you open an app and if you see an empty blank space, your user experience would be really bad. So there is a hard limit of 100 to 150 milliseconds, including the network latency between the user's app and exchanges and DSPs and so on. So there are tons of bid requests that are going through these exchanges and bidders every second. Usually we're talking about millions of requests per second, and this requires a really robust system that can handle a lot of requests per second. And the latency is a huge deal here. So every request has to be responded within 100 to 100 milliseconds. And that includes the time for making machine learning predictions, writing logs and things like that. So this requires a lot of state-of-the-art architecture and technologies and things like that. So it is a really huge business. And about my research, this is more related to game theory, actually. So let me give you an example again. So let's say you, after seeing 5 different advertisements, you decided to install some app. So these ads were about this specific app, maybe it's a game app. And after seeing 5 different ads, you eventually installed the game app. Now the question is, which of the 5 ads should get the credit? And if we actually have to split it, like how should we do it in a fair way? The reason for this question is actually very practical. If you have an advertiser who is, trying to, obviously advertise their newest game app to users, and this is you, so you eventually, after seeing 5 different ads, you decided to download this game app. So you've seen 5 different ads at 5 different times, and eventually you installed this game app. Now the question is, because you saw these ads and you were convinced to download the app, this advertiser will have to pay one of these 5, DSPs or bidders, because they work on behalf of the advertiser. So which one should get the money? Or if the advertiser were to split the money, like how should the credit be split? And this is a practical question, but interestingly, the way it works is typically companies actually use the last touch attribution, in the sense that if you clicked on any of these 5 different ads, then whichever ad you clicked on the last time. So if, let's say, you clicked the 4th advertisement and the 2nd advertisement, then this one wins because this is the one that you clicked last, assuming that this is the chronological order. So that's why this is called the last touch attribution. Now, if you didn't click on any of these, but you just saw 5 of them, and maybe you thought, oh yeah, so that game looks really good, so let me just go to App Store and download it. So if that happens, then the last ad that you saw would be the winner. So whoever sort of convinced you would be the last one that you interacted with in some sense. So this is the simplest attribution method, because it's really easy to declare the winner, who should take the credit if you install an app, right? On the other hand, this is clearly unfair, because everyone, maybe all these first 4 ads were really great ads that convinced you to download the app, but somehow this company, another company, showed one more ad just before you started. You decided to download the game app, and they take the credit. So in fact, this actually promotes a lot of frauds. And in mobile advertising, there are different kinds of frauds, and you can search for it and learn more about them. I'm not going to talk about those specific techniques here, but still, the one of the reasons I'm studying this is because the last touch attribution is so unfair that it actually promotes a lot of frauds. And I want to see if we can actually find more fair attribution that doesn't promote frauds and that is more fair to everyone involved. So in summary, I'm working on these 3 research projects. So the first one is about CS education and about how I teach my elective courses so that I can provide really great learning environment for my students, especially through the automated grading system and personalized feedback. The second research project, I want to focus on the problems of algorithm design, complexity analysis, and also game theoretic settings. So this is one of the research projects that I worked with along with students, 2 master's students. So one this past summer and another in the spring semester last year or earlier this year. And the third research project is actually in a brainstorming stage. So I'm still trying to figure out exactly how to formulate the problem, how to set up the model. And once that is somewhat settled, I want to gather some data, like actual data in terms of how many users downloaded a certain app after seeing what kind of ads and like when, and then whether we can utilize that information to come up with really fair attribution methods that can be used in practice. So if you have any questions or you're interested in research projects, please check out my website, because it actually has more details and references to some of the papers that I wrote. So you can take a look at them as well. And if you have any questions, feel free to email me at hlee84@usfca.edu. All right, that's it. Thank you everyone for joining. Bye-bye.